In this slow-motion tablecloth pull, the glasses drop vertically because the cloth's rapid acceleration is too brief to overcome the heavy glass's inertia. This outcome is the result of specific, consistent rules of motion. Dynamics is the branch of physics that studies these rules to explain why objects move. It allows us to move past physical intuition and calculate exact outcomes. Our goal is to apply Newton's 3 laws of motion to build a systematic method for solving mechanical problems. This approach provides a consistent framework for analyzing any object in motion. To follow this process, you will need a basic understanding of algebra and the ability to plot points on a standard 2-dimensional x and y coordinate plane. By combining these foundational tools, we can represent physical interactions between objects as a series of predictable equations. Newton's first law, often called the law of inertia, defines the foundational relationship between an object and the forces acting upon it. It states that an object will maintain its current state of rest or constant motion unless a force acts to change it. We can see this in the difference between surfaces. On a rough floor, friction acts as an external force that stops the puck. On a perfectly smooth air table, where that force is removed, the puck maintains a constant velocity in a straight line indefinitely. Newton's third law describes how objects interact. If a car pulls a trailer forward, the trailer exerts an equal and opposite force, pulling the car backward. A common mistake is to assume these paired forces cancel each other out. If they canceled, the trailer would never move. These forces do not cancel because they act on 2 different objects. One force acts on the car, and the other acts on the trailer. This law confirms that forces only exist as part of an interaction between 2 bodies. Mass, represented by the variable m, is an intrinsic property of an object. It measures the quantity of matter present, which remains constant regardless of where the object is located in space. Weight is different. It is a vector force found by multiplying mass by the local acceleration of gravity. While the mass of this block is constant, its weight vector shrinks on the Moon because the gravitational pull is weaker. The normal force is the perpendicular push an object receives from a surface it is pressing against. It is what prevents a block from falling through the table it sits on. Tension is the pulling force exerted by a taut string or rope. We can see how this force behaves using a heavy stone suspended by one string with a second string hanging below it. If you give the bottom string a sharp, sudden pull, the bottom string snaps first. The stone's inertia resists the sudden change in motion, preventing the force from reaching the top string. If you pull slowly, the tension accumulates and the top string breaks. For springs, we use Hooke's law. The force is proportional to the displacement of the spring and always acts as a restoring force, pulling or pushing back toward the spring's relaxed position. Identifying which of these specific forces are present is the first step in building a mathematical model of any physical system. To analyze this block being dragged by a cord, we use a free body diagram. This allows us to isolate the object and focus exclusively on the forces acting upon it. First, we represent the object as a single dot or point mass. Next, we superimpose an x and y coordinate system. Finally, we draw external forces as arrows anchored on the dot: gravity down, normal force up, and tension pulling at an angle. This diagram translates the physical setup into a geometric map, which we can now use to write our equations. Newton's second law, force equals mass times acceleration, is the engine we use to solve the diagram. We analyze each axis separately, splitting the tension vector into horizontal x and vertical y components. On the y-axis, upward forces and downward gravity balance out, so vertical acceleration is 0. On the x-axis, the horizontal force is the net force causing acceleration. By isolating the axes this way, we turn a 2-dimensional problem into 2 simpler 1-dimensional calculations. We have successfully taken a physical event, reduced it to a point mass, and used the vector components to find an exact acceleration. This process works for any dynamics problem. Identify the object, draw the anchored free body diagram, split forces into x and y, and apply the second law. You can apply this right now to your own body. As you sit in your chair, your downward weight is being perfectly countered by the upward normal force of the seat. Viewing the world as a system of interacting vectors makes the mechanics of movement predictable. Once mapped, the motion follows the math.